When you picture a telescope, what do you see? Perhaps an antique device comes to mind, an old, brass or wooden cylinder with glass lenses, reminiscent of the tool Galileo Galilei famously used. With his rudimentary telescope, Galileo revealed Jupiter's moons and revolutionized our understanding of the cosmos. Or, perhaps you envision the enormous telescopes housed in vast domes atop mountains in Chile or Hawaii, their mirrors so massive they could cover a tennis court. These grand machines seem almost alive as they gather secrets from the universe. Alternatively, you might picture the iconic Arecibo radio dish in Puerto Rico, which once captured faint radio waves from distant cosmic sources, giving us a way to listen to the stars. But there's another telescope, far different from these classic images. It doesn't gaze into the sky, but instead lies concealed deep beneath the frozen surface of the South Pole. Imagine a vast, cubic kilometer of ancient, untouched ice. This is IceCube, a telescope hidden from view under the Antarctic ice, designed to capture not light but one of the most elusive particles known, the neutrino, often referred to as the ghost particle. Today on University of Universe, we're delving into the mysteries of the IceCube Neutrino Observatory, where scientists work in the extreme cold to detect these remarkable, enigmatic particles. What are neutrinos? Imagine standing on Antarctica's surface, unaware that some of the rarest cosmic events are being observed right below your feet. The IceCube Observatory resides at the Amundsen-Scott South Pole Station, Earth's southernmost human-occupied outpost. Here, researchers use the icy depths of Antarctica itself to trace high-energy neutrinos that traverse our planet from deep space. Why go to such lengths to build a telescope under harsh, freezing conditions? The answer lies in the unique nature of neutrinos. These particles are as fundamental to matter as electrons or quarks, but they interact so weakly with other particles that detecting them requires an extraordinary approach. Most neutrinos that reach Earth come from our Sun, created by nuclear fusion reactions within its core. Others, however, have violent origins, formed in supernovae, cataclysmic collisions, or near black holes. Neutrinos belong to the lepton family, a group that includes electrons. Like electrons, they are not affected by the strong nuclear force, the interaction responsible for binding atomic nuclei. Yet, unlike electrons, neutrinos are electrically neutral and incredibly light, with a mass so small it remains one of particle physics' greatest challenges to measure. Because they have no electric charge and such little mass, neutrinos interact only via the weak nuclear force, giving them an almost ghost-like quality. They pass through matter nearly undisturbed, making them difficult to detect. Scientists typically catch a glimpse of them only through the rare interactions they have with other particles. To understand just how elusive neutrinos are, consider this: a single neutrino could pass through Earth without interacting with a single atom. Trillions of neutrinos pass through your body every second, yet only about 1 in a billion will interact with an atom during your lifetime. Many of these neutrinos originate from the Sun, but others come from powerful cosmic sources like supernovae and black holes. This ghostly ability to pass through matter sets neutrinos apart from photons, or light particles. In the Sun, photons take around 1 million years to journey from the core to the surface, repeatedly scattering off atoms in the dense solar material. Neutrinos, however, escape from the Sun almost immediately, traveling through space at nearly the speed of light. This unique trait allows neutrinos to carry unaltered information from the universe's most extreme and energetic processes. The IceCube Observatory, a new kind of telescope. Beneath Antarctica's surface, IceCube's 5,160 digital optical modules, DOMs, are suspended in a three-dimensional grid between depths of 1.5 and 2.5 kilometers, in a part of the ice shielded from sunlight. These modules are not traditional light detectors. They capture light generated by neutrino interactions occurring within the ice itself. When a high-energy neutrino collides with an atom in the ice, it generates a cascade of particles, emitting a faint flash of blue light. This light, called Cherenkov radiation, occurs when particles travel through ice faster than light does within that medium. When IceCube's DOMs detect this blue glow, scientists know a neutrino or a cosmic ray has just traversed the ice, and they work to trace its origin. At the core of this particle cascade is the production of a muon, a particle capable of moving faster than light within the ice. As it races through the ice, the muon emits a cone-shaped burst of Cherenkov radiation, similar to the sonic boom of a supersonic jet. This blue light allows scientists to identify the paths of neutrinos, acting as a signal guiding them back to their cosmic sources. Cherenkov radiation has a haunting blue glow, often seen in nuclear reactors. Here, under the Antarctic ice, it illuminates neutrinos' presence. The DOMs are designed to detect even a single photon of this eerie blue light, and the tiny time delays in each DOM's detection of this light enable scientists to reconstruct the neutrino's path through the ice. Technological innovation at IceCube. The DOMs are incredibly sophisticated devices housed within 13-inch glass spheres to withstand the crushing pressure and extreme cold of the Antarctic ice. Each DOM contains a photomultiplier tube, sensitive enough to detect a single photon, transmitting over a terabyte of data daily to researchers worldwide. Among the countless neutrinos streaming through space, IceCube detects around 275 events daily from cosmic sources outside our galaxy. However, distinguishing neutrinos from cosmic rays, high-energy protons, and atomic nuclei from space remains challenging. Cosmic rays create background noise, making it difficult to identify true neutrino events. Yet, every so often, IceCube detects a high-energy neutrino from a distant, extreme source. In September 2017, IceCube detected an unusually intense Cherenkov radiation burst from a neutrino. Tracing its path back to its origin, scientists discovered it came from a blazar, a galaxy with a supermassive black hole emitting a jet of particles toward Earth. This event was groundbreaking, marking the first time IceCube coordinated with observatories around the world, allowing them to observe the phenomenon in real time. The detection heralded a new era of multi-messenger astronomy, where cosmic phenomena are studied not only through light but also through gravitational waves, cosmic rays, and neutrinos. A breakthrough in understanding the universe. IceCube has opened an entirely new window for observing the universe. Like gravitational waves, neutrinos can travel unimpeded by obstacles that would absorb or scatter light. They provide insights from deep within powerful cosmic events, giving scientists a fresh perspective on the universe's most energetic occurrences. IceCube's role as an alert system for global observatories brings cosmic phenomena into focus that we would otherwise miss. Building IceCube was a monumental achievement, requiring 7 years of work and drilling 86 holes over 2.5 kilometers deep into the Antarctic ice. Scientists melted each hole with 750,000 liters of hot water to deploy the DOMs. A dedicated team of scientists braved extreme Antarctic conditions to operate the observatory, hoping to reveal more about dark matter, fundamental particle properties, and even the nature of ice itself. Despite the vast strides made with IceCube, neutrinos remain one of the greatest mysteries in particle physics. With each new detection, scientists draw closer to uncovering their secrets, and, in turn, understanding the forces shaping our universe. Detecting a single neutrino is an extraordinary feat, symbolizing humanity's drive to understand the powerful forces shaping everything around us. IceCube is transforming our grasp of the cosmos, allowing us to see the universe in new ways. We have entered an age where we observe the heavens not just through visible light, but through particles like neutrinos, which carry messages from distant, violent events that light alone cannot convey. The IceCube Observatory stands as a testament to human curiosity and innovation, shining a new light, blue and ghostly, into the depths of the universe.